Heat waves, drought, tornadoes, hurricanes, floods, blizzards, bitter cold. Extreme weather has an incredible impact on people across the globe. On Mount Washington, our scientists brave some of the worst weather on the planet to improve our understanding of our warming world.
Sorry about that, folks. It looks like my microphone wasn't working before. Apologize to everyone. Well, tonight we have Alex Contosta and John Campbell, who are tonight's speakers. We're going to talk all about winter weather whiplash. So apologies if I'm repeating myself a little bit here, or if you missed it. If you have questions tonight, make sure you use the Q&A button. You can find that at the bottom of your Zoom toolbar. And if you'd like to, if you're joining us through Facebook, you can put some questions in that way as well. We'll follow up following the program here and respond as quickly as we can, though apologies if we can't get your question during the program. If you want to sign up for a future Science in the Mountains program through Zoom, make sure you sign up through mountwashington.org/SITM. All righty, well, apologies again for the microphone issue there at the beginning. Thanks to all of you who helped point that out. You can test as much as you like, but still run into issues. Anywho, before we introduce tonight's speakers, who will be talking all about winter weather whiplash, we have some trivia questions for you all. If you're participating on Zoom, you should be seeing some poll questions come up right now in front of you here. Always curious, the first question, where you're joining us from. If you're joining from a state within New England, if you're joining from outside of New England, or maybe even outside the country, love to know where you're joining from, always curious. Question number 2, wondering, have you attended a Science in the Mountains program before? Could be your first program. Maybe you've been to a couple, maybe you've been to many. Always curious to see how many people are following along. And then we have 2 trivia questions this evening from our speakers. In fact, a couple tough ones. The first one is, what is winter weather whiplash? I won't go through all of the responses there, but all having to do more or less with different shades of drastic changes in weather over a short period of time. Let's see how you respond to that one. And then our last question here, what is the latest ice out date? Meaning, what is the latest that ice has more or less completely melted during the 136-year record on Lake Winnipesaukee in New Hampshire? So for those of you outside the region, one of the largest lakes here in the state of New Hampshire, with a record going back 136 years. Was it March 18th, April 18, March 20th, or as late as May 12th for the latest ice out date in that 130-year record? Alrighty, well, it looks like many of you have participated, but I'll give you another 5 seconds or so to get your responses in, and we'll end the poll soon, just in 3, 2, 1. Alrighty, we'll end it right there and see how you all did. Let's see. So for those of you, if you can see it on your Zoom screen, it looks like the majority joining from the great state of New Hampshire. Welcome. Although I shouldn't say the majority, most are actually joining from outside of New England. Welcome to all of you. Great representation all throughout New England as well. And then even one participant from outside the country. Welcome, welcome. Thanks. Glad to have you with us this evening. For those of you curious about if you've attended the program before, pretty evenly split. In fact, look at that, almost 30% of you. This is your very first Science in the Mountains program. Welcome, glad you can join us tonight and hope to see you again for a future program. And thanks to all of you who have participated in the past. And then on to our trivia questions. Well, yeah, like I said, these are some tough ones. Somewhat evenly split, although no, actually 60% of you saying that winter weather whiplash is a sudden and drastic shift in temperatures from warm to cold or vice versa within a short period there. And then last but not least, what was the latest ice out date? Most of you said May 12th. Okay. Well, I actually don't know. Well, I kind of know the answers a little bit. I was talking with our speakers about this before, but I'd love to welcome both Alex Contosta and John Campbell, our speakers for this evening. If you both are there, can turn your cameras and mics on. Hey, John, I can see you nicely. Hey, Alex, welcome, welcome. You guys didn't tell me my microphone decided to die right after we tested it. What was that all about? Go figure. Welcome to both of you. And Alex, right out the gate, this was really intriguing. I usually ask speakers to help us with some trivia questions. And I suggested, I don't know, maybe you can just ask the question, what's winter weather whiplash? And you came up with some interesting, and I would say maybe unfair question or answers there. How did you come up with your question and what's the right answer?
Yeah, so first of all, thanks for having us. I should say that it wasn't me who came up with the answers. I thought I would try seeing what happened if I asked ChatGPT, the AI tool, artificial intelligence tool that's been in the news a lot, what it would say, right? I've been curious about it and I haven't interacted with it at all. And I teach at the University of New Hampshire, and that's been a big discussion among faculty right now. So I thought, this could be an interesting test case. And so I downloaded the software and typed in the question, what is winter weather whiplash? Or I think I said, give me 4 definitions of winter weather whiplash. And those are the 4 that it came up with. And I would say they're probably all sort of right and sort of weird, but I think that's okay because I think winter weather whiplash is sort of an odd phenomenon. And so we'll get to that, but that's the history behind my question and the answers.
Well, it was a tough question, but the good news is everyone was right if you participated. Yeah. So that's good. And John, what about your question?
Yeah, so my question was, what is the latest ice out date in the 136-year record from Lake Winnipesaukee? And the answer is May 12th, which I think most people got. It actually happened in 1888, a year after the record started. March 18th was another answer, and that was the earliest ice out. And then April 18th is the mean, and April 20th is the median.
Oh, excellent. Yeah, so some thoughtful wrong answers, I guess, that you put in there. Those are some tough ones as well. My goodness. Well, thanks everyone for participating in the poll, and thanks John and Alex. At this point, why don't you take it away? We'd love to hear all about this very timely topic of winter weather whiplash.
Are you seeing the right screen?
Yes, but now you need to swap your presenter view.
Okay, all right, that's what I was asking. See, we tested this before as well, and now we're doing it again. All right, how about now?
Yes.
Okay,
that's great.
Excellent.
All right, well, I guess I'll get us started here. I'm John Campbell. I'm a research ecologist with the U.S. Forest Service. I'm based out of our Forest Service office in Durham, New Hampshire, and I'm the project leader for the Hubbard Brook Experimental Forest, which is in the White Mountain National Forest in North Woodstock, New Hampshire. And so many of the examples and some of the data we'll be showing today come from that site. I'm fortunate to be here with Alex Contosta. Alex is a research assistant professor at the University of New Hampshire, and so we'll be giving kind of a joint presentation. And today, as Brian said, we're going to talk about winter weather whiplash events, which we've been studying. Alex and I have been studying together for a number of years now. I'm going to start the presentation off by just giving a little teaser of some observed changes in climate that we've been seeing in New Hampshire. And I'll talk a little bit about extreme weather events. And then Alex is going to talk more specifically about what we call winter weather whiplash events, which are a specific type of extreme event that she'll explain more about shortly. Go ahead. So it's clear that the climate is changing in New Hampshire and really across the broader region. This graph shows air temperature trends at Hanover, New Hampshire, which is the gray line. This is one of the longest records around. It dates back to the late 1800s. I've also plotted data here from Mount Washington in black and Hubbard Brook in blue. And these are the average yearly air temperatures at each site relative to a reference period. And so by plotting them this way, it lets you overlay sites with very different temperatures. It's obviously a lot colder on Mount Washington than Hanover, but by plotting them this way, we can kind of compare them. You can see that they all track each other very closely, and all sites are showing pretty substantial increases in air temperature, anywhere from about 0.2 to 0.5 degrees Fahrenheit increase per decade. Winters are warming faster than other seasons. At Hubbard Brook, annual average air temperature has increased by about 2.5 degrees Fahrenheit since we started making measurements in the 50s. And in winter, it's increased by about a degree more than that, so about 3.5 degrees Fahrenheit. Go ahead. We also seem to be losing our extremely cold temperatures. So here we've divided temperature into different classes that range from -25 degrees Celsius up to +25 degrees Celsius. If you're more comfortable with Fahrenheit, it's from about -13 degrees Fahrenheit up to 77 degrees Fahrenheit. And these orange bars indicate the percent change in the frequency. And so basically what this means is that the number of cold days has decreased and the number of warm days has increased. So we've seen about a 40% decline in the number of these really cold days and about a 5% increase in the warm days with warm temperatures. So the loss of these really cold temperatures is greater than the increase in warm temperatures. And this is really important to us and really has an impact on ecosystems. Some invasive species are knocked back by really cold temperatures. An example of that is the hemlock woolly adelgid, which I'm showing in this image here. This kills hemlock trees. It doesn't do well at temperatures below about -5 degrees Fahrenheit. And so those cold temperatures knock down the populations. The ranges of native species are also affected by these extreme temperatures as well. So losing these cold temperatures really has the potential to change the species composition and the character of our forests. When we talk about climate change, people immediately think about temperature, but precipitation is also part of the story. Compared to temperature, precipitation varies much more from year to year, but we're seeing clear evidence of increasing precipitation in New Hampshire at Hubbard Brook, where we started making measurements in the 1950s. Precipitation has increased by 14 inches since that time. So it's getting more, we have more than a foot increase in precipitation over this record. That's really remarkable. We see similar trends at Hanover. The record is a little more patchy. It's not quite as steep, but still we see these increasing trends, and it's true in the southern portions of the state as well. And of course, this increase in precipitation has been causing a lot of flooding, which I'm all sure you're well aware of. Unlike air temperature, most of the precipitation change is happening in the summertime. and we don't see any significant change in winter precipitation. Next slide. So if we have warmer winter air temperatures and no change in the amount of precipitation falling during winter, it's not surprising that our snowpack is declining. At Hubbard Brook, technicians go out every week and they measure the depth and the amount of water that's stored in the snow using these snow tubes. It's been done the same way since the record was started back in the 1950s. And you can see that the snowpack is declining. This graph shows the maximum snow depth that we've measured each year, and it's declined by about 11 inches over this record. And the same is true for what we call the snow water equivalent, or the amount of water that's stored in the snow. Next slide. We have other indicators of winter climate change as well, including ice in and ice out dates, as I mentioned with the ice out dates on Winnipesaukee. These data are from Mirror Lake in North Woodstock, New Hampshire, where there's a record that dates back to the late 1960s. Of course, people weren't thinking much about climate change when these records began, and yet they've really become a valuable valuable indicator of climate change, because they give an integrated signal of the entire winter period. And both ice in and ice out dates have changed over time. In this case, the ice in date is recorded when 50% of the lake is frozen and remains frozen. And the ice out date is when 50% of the lake melts and remains unfrozen. And so basically a technician climbs up to the top of the hill, looks down from this vantage point over the lake, and makes the call whether ice in and ice out date has occurred. So the ice in date has shifted by 5 days. It's occurring 5 days later in spring, and the ice out date has shifted 10 days earlier. And so, I'm sorry, ice in date has occurring 5 days later in fall, and the ice out date is occurring 10 days earlier in spring. And so the changes in spring are greater than the changes in fall. Next slide. The difference between the ice in and ice out date, of course, is the number of days of ice cover. And so this graph just shows the number of days when there's ice covering the lake. It's declined by 15 days over this record. And I think what's really interesting about this graph is that not only has the ice cover declined, but it's also getting more variable. So the ups and downs are getting bigger and bigger over time. And that's part of the climate change story, is this increase in variability. In fact, in 2018, it was a really strange year. It was the first time the lake completely froze over in the fall and then completely melted and refroze again. Once the lake freezes, it usually stays frozen, and 2018 was the first time in the record that the lake ever froze, melted, and then refroze. And so I want to kind of build on this idea of variability and talk about extreme weather events. And what we mean by extreme weather events is weather that's outside of the range of what we consider to be normal based on our historical conditions. A lot of the recent research on climate change has shifted away from looking at long-term trends, like I've been showing so far in the slideshow, and moving toward evaluating extreme weather events. And I really think the reason for that is that even though these subtle changes in climate over time are important, people really feel the effects of extreme weather events. And so these events can cause damage and are what people remember and care about. It's important to recognize that we've always had extreme events. So they've always been a part of the picture and are not really a sign of climate change on their own. But there are indications that climate change may be increasing the frequency and severity of these events. And so that's really the connection between extreme events and climate change. Next slide. When we talk about extreme weather events and climate change, we often think of droughts and floods and heat waves. And there's pretty convincing evidence that climate change is impacting these types of events. For other events like hurricanes and tornadoes, in our region, I'd add ice storms to that list. the connection between climate change and these events is not as clear. And I think part of the reason for that is that we don't understand these events as well. They're rare and difficult to predict, so it's difficult to link the changes in frequency and severity of these events to climate change. Next slide. In comparison to some of these other types of events, there's been much less work done on extreme winter events. This year is a good example of a kind of a wacky winter. We've been having at Hubbard Brook, we had one of the lowest snow years up until about 2 weeks ago. We also had a cold snap where it got down to negative 31 degrees Fahrenheit. It came close to our all-time record of negative 35 degrees. That lasted for 1 day, and then temperatures quickly rose and were seasonably or unseasonably warm. And so these types of changes back and forth are kind of typical now and are a phenomenon we've been seeing. And this is just a clip from the Associated Press about a snowstorm in 2017 in Boston, where there was a foot of snow, which was followed by temperatures the next day that were in the 50s and 60s. And this is what we mean by winter weather whiplash. And Alex is going to talk more about that now. And so, Alex, I'll pass things off to you.
Excellent. Thank you. Okay, so I have a definition of winter weather whiplash up here on the screen that I'll offer. And this is a definition that I think touches on the ones that ChatGPT gave us. But you know, we've been working on this for the last few years, this concept of winter weather whiplash. And the definition that John and I and some of our other colleagues came up with was that it's a class of extreme event where you have a collision of unexpected conditions. And this produces a forceful, rapid, back and forth change in winter weather and induces an unexpected impact on natural and/or human systems. And so you can think about if you've ever been rear-ended, and I'm sorry if you have, but you know, the force of the collision can sometimes like physically move your body back and forth. And that's what we're sort of talking about. We're talking about whiplash, this very forceful, rapid back and forth change in winter weather, which could be, you know, encapsulated by this really big snowstorm followed by temperatures in the 60s the next day, right? And we propose that these unexpected and forceful changes can have these big impacts on natural ecosystems, on human systems, and on coupled natural and human systems. Okay, here we go. All right, so we have identified 4 types of winter weather whiplash events, and this picture is just showing these 4 types of events. So on the top, you're looking at time. And so winter weather whiplash events can happen in the fall, they can happen in the winter, and they can happen in the spring. And regardless of time of year, these events are defined by this whiplash, this crossing of the threshold that delineates the freezing point of water. So here I have it marked as 0 degrees C. You could think about it as 32 degrees Fahrenheit. But if you have an early season snowstorm in the autumn or a cold snap in the spring, that would be defined by this, you know, back and forth crossing of the freezing point of water. It's warm and then it's cold, or it's cold and then it's warm. You have this back and forth phenomenon. In the winter, when we have sort of normal winter conditions and it's supposed to be cold and it's supposed to be snowy, you could have a heat wave, anomalous warmth. Maybe it gets to 60 degrees in February, or you have a really large rain event on top of snowpack. And so you can have winter weather whiplash events in spring, in fall, or in winter. And I'm going to talk a little bit about the kinds of events that can happen in winter first. These would be winter heat waves, so really anomalous warmth, or rain on snow events where you have a rainfall that happens on an already existing snowpack. Okay, so let's look at some examples of these kinds of events. You get a sense of what we're talking about here. So here I'm showing a picture that was taken at one of Our research site's close to the University of New Hampshire's main campus. This is a picture that you might think was taken at the end of March or in early April, because the snowpack is obviously melting. But in fact, this picture was taken in late February of 2017, where we had record-breaking temperatures that were in the 60s and 70s. And so this period of time has been called the winter heat wave of 2017. We saw these anomalously warm temperatures across the region. And this event presented some major economic losses for winter recreation and tourism. We're in the first full week of March right now, but we just got finished with the February vacation weeks when a lot of people go skiing in New England. And so if you have a really prolonged period of anomalous warmth, this can be really damaging to ski areas and other areas that rely on winter visits for tourism. You can deal with potential losses of life as people fall through the ice if it's not thick enough to bear weight. Rapid melting during these heat wave events can lead to flooding. If you're releasing a lot of snow meltwater into rivers, especially if these rivers aren't flowing freely because they still have ice in them. And then rapid warming can also lead to ecosystem impacts. All the microbes and roots that are in the soil, whose activity is pretty slow in the winter, if you have rapid warming, they can wake up and they start to breathe. And as they breathe, just like we do, they release carbon dioxide into the air. So that's an example of the winter heat wave phenomenon that you might find during winter. Another type of winter weather whiplash event that you can have in winter is a rain on snow event. And so here I'm showing a picture from the rain on snow of 2016, where rainfall totals of about 2.7 inches or 68 millimeters fell on top of deep snowpack and melted huge amounts of ice and snow across Vermont and southern Quebec. And as you might imagine, you can experience lots of flooding from these kinds of events just from the sheer volume of meltwater, but also because of the same phenomenon I already talked about, where you don't have rivers freely flowing and can get backed up as they receive a lot more meltwater, and then you can get lots of impacts as a result. You can also get lots of acidity and nutrients flushing from uplands into aquatic systems when you have these big melt events, and that can have impacts on water chemistry and ultimately on water quality. So those are two examples of events. Winter weather whiplash events can happen within winter, but then we also know that winter weather whiplash can happen in the shoulder seasons. So they can manifest in the autumn and in the spring if you have an early season snowstorm or a late season cold snap in the spring. And so I'm just going to show you a couple of examples of how we've thought about these events with real world circumstances. So here's a picture of ice that's on coating some apple trees. This is meant to depict the fall spring of 2012. So this is a winter weather whiplash event that happened outside of winter. And the story here was that vegetation throughout the Northeast experienced early leaf out due to record-breaking high temperatures in March. And so we had all these plants that had all this like newly emergent, very sort of vulnerable tissue, and then the spring frost damaged this tissue. Orchards experienced billions of dollars in economic losses, and the fruit crop was very poor as a result of this damage. But it wasn't just fruit trees that experienced this damage. We also had lots of forest species that were damaged by the spring frost and were never fully able to recover. And so their ability to perform photosynthesis, to take up carbon from the atmosphere was compromised by this event. So we have lots of impacts to human systems and to natural ecosystems from this. And then we can also have early season snowstorms. This would be another example of a winter weather whiplash event that happens outside winter. Some of you may remember the Snowtober of 2011, where we had a nor'easter that dumped a lot of snow right before Halloween. And this resulted in widespread tree mortality, lots of damages to businesses and homes, lost power, Halloween was canceled, lots of impacts associated with this. So, we have our definition for winter weather whiplash. We develop a typology of events, and I've shown you some examples, but one of the challenges that we have been trying to grapple with is how do we translate these types of events, this typology, into a quantitative approach for identifying winter weather whiplash events? Can we identify these events in the historical record in order to understand how they might be changing over time? And so one of the ways that we approached that was by using the Hubbard Brook ecosystem study as a model system. So John already talked about that a little bit. This is a site that's located in the White Mountains. And it's really fantastic in a lot of ways, but one of the ways that it's great is that it has this long-term record of air temperature, precipitation, snowpack, stream flow, and we can use this long-term record as a way to try to develop approaches, develop metrics for quantifying events. Hubbard Brook has also been monitoring vegetation phenology, or sort of some of the greenness that forest canopies develop as they go through spring into summer, and then the greenness that they lose as they progress through fall. And that's really important for identifying winter weather whiplash events that happen outside of winter, right? Because some of them can happen in the spring or the fall. And they haven't been doing this for quite as long, but still a pretty long time. And we have developed a bunch of different ways for trying to identify winter weather whiplash events. Some of them are using a principle of trying to identify events based on how extreme they were, how extremely warm air temperature was, or a rainfall event was in the winter compared to the historical baseline. So we've done a lot of that work, and then we've also done some research into the scientific literature, trying to understand if there are, certain hard thresholds that might have to be crossed. If air temperatures have to reach a certain amount of warmth, or if a certain amount of snow needs to fall for an impact to happen, right? Like an event could be identified based on how extreme it is, or how much it's able to cause an impact. So we've sort of played around with both of those approaches. And I'm going to show you a graph of what we have come up with using both of these based on the record at Hubbard Brook. And this is a little bit of a blow your mind kind of series of graphs. It's quite busy, but I think if we step through it together, it'll make sense. What you're seeing here is 4 different graphs, 4 different panels. And each panel is showing you one of the events that I already talked about, right? One of the 4 examples of winter weather whiplash. We have the 2 events that happen outside winter on the top, the 2011 Snowtober snowstorm and the fall spring of 2012. And then the 2 events that happen in the winter on the bottom, the 2016 rain on snow event and the 2017 winter heat wave. And for each of these, there are lots and lots of variables plotted. We're looking at temperatures, and that's minimum and maximum. We're looking at snow water equivalent. John already talked about that. So the amount of, so snow depth quantified by how much water is in that snowpack. And we're looking at rainfall. We're looking at snowfall. We're looking at this phenology index of greenness. So if you're 4, that means that you have full greenness. It's high summer, the forest canopy is closed. If it's 0, that means it's the dormant season. Along the x-axis, the horizontal axis of all of these is the day of the year. So day of year 1 is January 1st, and that's in the middle. And then if you go to the left of that, you're in the fall, and the right of that is the spring, right? And then you might notice that, you have these dark lines, like dark red for maximum temperature. And that would be the maximum temperature for that year, for each day of year for that year. And then the shaded area around it would be all of the possible temperatures for that day of year over the entire record, right? So there's a lot going on. But what I really want to key your eyes into is that each of these graphs has a circle around a cluster of points. And so on the top left, the 2011 Snowtober snowstorm has these purple points that are circled, and that's showing the snowstorm, right, that we experienced. that we were able to detect using either some index that measured how extreme the event was, and that would be, you know, whether across the 90th percentile of, you know, the historical baseline, or, you know, using some sort of value that we were able to pull out of reading a lot of papers and trying to understand like how much snow would have to fall and what leaf area to cause an impact. And so the take home message here is that, you know, we developed a bunch of different approaches for trying to pick out these events, and we were sort of successful at that, right? So we were able to find these events. You know, we see the 2011 Snowtober snowstorm. Hopefully you can see my mouse moving around. We see the fall spring of 2012, this cluster of points that's identifying that event. We see this 2016 rain on snow, and then we see the 2017 winter heat wave, plus a lot of other events. But we feel like, you know, pretty good about this approach from being able to pick these events out of the record at Hubbard Brook that we know have occurred, right? And so that's good. But, you know, the next question is, okay, if we can identify these events, it would also be nice to be able to identify some of their impacts quantitatively, because I told you some stories, but it would be also good to look at some data. So I'm just going to go through a couple of case studies quickly, and then we'll wrap up. So the first one I'm going to show you is a quick case study of the impacts of winter weather whiplash during winter. And here we're trying to understand what are the impacts of rain on snow and winter heat wave on stream flow. And how does this manifest in catchments or watersheds that have various sizes and are across different climate areas? So we collected data from a bunch of different sites, scattered mostly throughout the Northeast, but then we have our site in Canada. And these sites vary in their mean winter temperature. So, you know, Hubbard Brook and Biscuit Brook would be the warmer ones, and this area up in Ontario would be the coldest one. And we, you know, use the long-term climate records from these sites to try to identify events in the same way that we did at Hubbard Brook, where we sort of piloted our methods. And what we see is that some of the highest flows that were detected at these sites were associated with rain on snow events. So this table is broken up into the different sites that we're looking at and the different types of winter weather whiplash events, rain on snow or winter heat wave, and how many annual max flow events were associated with these winter weather whiplash phenomenon. And especially at you know, Biscuit Brook and Hubbard Brook, we see that some of the highest flow events that happened during that year, you know, over the years, were associated with rain on snow events. And so these rain on snow events actually do drive really high flows that could have potential impacts for flooding. The second case study was focused on the 2011 Halloween nor'easter or Snowtober snowstorm. And here we're trying to do a little bit more of a socio-ecological analysis that looks at natural and human systems of this winter weather whiplash event that happened outside of winter. And so for those of you who don't know about this storm or need a reminder, this was a classic nor'easter that hit the northeastern United States between October 29th and 31st, 2011. Here's just a satellite view of the storm. It was a pretty unusual storm. The form of precipitation itself was unusual for that time of year, and the snowfall totals broke records in some places, regardless of, you know, time of year, just, you know, record snowfall ever at the time of the storm. And so these areas that are in red and orange are seeing the highest snowfall totals, and then the areas that are in blue and purple had less snow. But one thing that's important to consider is that this snowfall happened at the same time that a lot of other conditions were happening. So soils were saturated following an extremely wet period where it had rained a lot. Residents that were, you know, experiencing some of the biggest snowfall amounts were already feeling a lot of storm fatigue because Superstorm Sandy had just happened. Many trees were still in leaf because the fall had been very warm and it delayed fall senescence, or the process of trees losing their leaves, especially for oaks and beeches that tend to go through senescence later and also hold on to their leaves even if they already have lost all their color. And then the big thing to keep in mind is that this is also happening at the same time as Halloween. And if you're a kid, this is the biggest candy night of the year. And if you're not a kid, it's also a big party night of the year, which has economic implications. And so this combination resulted in a lot of impacts. 4.2 million people lost power, and some of those power outages lasted for over a week. There were 39 deaths, extensive tree damage, suspended air, rail, and road travel. Halloween was either delayed or fully canceled, and there was over $3 billion in total costs. And so we were really interested in trying to develop an approach that really grappled with, the drivers of the storm, tried to encapsulate some of those different variables that went into making the storm so difficult, and some of the impacts of the storm. And so to do this, we sort of combined a bunch of different approaches. So we looked at newspaper coverage of the storm from more of a qualitative view of the impacts, considering themes of the weather, power outages, public safety, tree damage, community responses, local events. Read a lot of papers and pulled out a lot of these themes that were very common related to storm coverage of the event to get a sense of what some of the impacts might have been that may be more difficult to tally in terms of dollar amounts. And I'm just going to give you a flavor of what some of this looked like in terms of the results. So, if you're thinking about power outages and thinking about what those impacts look like, here's a quote from the York Daily Record that says, since Saturday, local and regional linemen have struggled in 16-hour shifts to repair power lines damaged by tree branches weighed down by wet snow and leaves. It's called cracking. This storm hit when not all the leaves had fallen, and that extra weight causes the branches to crack and fall on the lines. The biggest challenges are the trees. When the branches come down, they snap the lines in half. And then when thinking about the impacts on local events, you could find, lots of types of information like this. So here's a quote from the New York Times on November 4th that says, when I found out Halloween was canceled, I was so bummed. It was the worst day ever. I went over to my grandparents' house because they were like the only people on the planet who had no power. Obviously, this is a kid. We still didn't get to go trick-or-treating. There were too many trees and wires all over the place. So I sat there on the couch and did nothing. I said, I can't believe it's Halloween and I'm sitting on a couch. This is an outrage. Which we can sort of laugh at this, but I think it's also reinforces this idea that these whiplash events can have impacts on ecosystems, on people, on infrastructure. They are, I think, what we experience very viscerally. John talked about this already, and some of the impacts are really hard to quantify in dollars, which is sort of why we went after this mixed methods approach. We also wanted to really more quantitatively understand the drivers and impacts of this event. So to do that, we did some more statistical modeling where we combined meteorological data like snowfall totals, natural system data like what was the leaf area index, what was the leaf area at the time of the storm, and then some human system variables that seem to really matter in terms of impacts like road density, population density, income, social vulnerability. How do these ingredients combine to try to predict the impacts of this storm, which here we're talking about in terms of number of newspaper articles or sort of the coverage. And the take home from this is that, we can predict impact of the storm if we know the snowfall total, the road density, the leaf area index, and the income, right? All of these factors really matter, and that's what this figure is showing. But I think the even bigger take home of this work that we've been doing, trying to understand the drivers and the impacts of these winter weather whiplash events, is that it's important to consider all of these. So this case study really highlights the need to consider the meteorological driver, how much snow, right? But also some of the natural system drivers, how many leaves were on the trees, and some of the human system drivers, right? Where are the power lines? Where are the roads? Where's the social vulnerability? And not just the weather drivers alone. So I'm going to wrap up here so we have time for some questions. So just to sort of bring us full circle, we define winter weather whiplash as a class of extreme event where we have this collision of unexpected conditions. Snow is falling on leaves that still haven't dropped. It's cold when leaves have just emerged from the trees. Rain is falling on deep snowpacks. It's super warm in February, right? We have this collision of unexpected conditions. And this features a forceful, rapid back and forth change in winter weather. Usually this crossing of the threshold at which water freezes above and below 0 degrees Celsius or 32 degrees Fahrenheit. And it produces an unexpected impact on natural systems, on human systems, or the interaction between them. And our goal is really to try to develop a deeper understanding of these events and impacts to try to minimize their risks, right? There are lots of impacts of these events that we'd like to try to mitigate if possible. Some of our future work is trying to take the work we've done so far, and try to develop ways to detect these events and quantify their frequency and severity, not just at Hubbard Brook, but across Eastern North America, and really understand whether or not they've changed through time. And also just a reminder that we're looking at impacts, right? Not just trying to identify the events themselves, but trying to identify their impacts, or maybe even use the impacts as a way to help us identify the events. Focusing on winter weather whiplash that happens in winter, that happens outside of winter, because both are really important. And I just want to say thank you to all of you for showing up tonight, to the members of our team, some of whom are in this picture here, and then all the funding that has supported this work. And I think we'll take questions.
All right, thanks so much, Alex. Thank you, John. Really appreciate you sharing your work so succinctly. I know it's hard to cover everything you've both been working on over the years here, but thank you for boiling it down and for having some really nice concrete examples as well for everybody. So as Alex suggested, we'd love to take some questions. If you're joining us through Zoom, make sure you get your question in using the Q&A button at the bottom of your toolbar there. If you're on Facebook, we'll try and get your questions after the program and can always pass along questions after the fact. We'd be happy to do that. But we already have some great questions. And so let's just get right to it, because there's some really thoughtful questions that folks have been already offering here. And so I'm not sure who I may offer this one to first. Maybe, I don't know, maybe, well, I'll just say, John, how about you take a stab at this first one from Jack, who asked a question around Hubbard Brook and sort of time scale. I know, in some of the time series, you were looking at Hubbard Brook going back to the mid-50s. Jack is asking, well, if data only goes back to 1956, this is obviously data can go longer, but what considerations do you have around timescale? I mean, obviously, I think you'd like to have more data always, but does that limit, I guess, any of our understanding of the long-term, I guess, implications of winter weather whiplash?
Yeah, it's a great point, and I'm glad he brought that question up. So Hubbard Brook certainly doesn't have the longest records, meteorological records in the Northeast. And I pointed that out just by showing, the records from Hanover, which are much longer records. We're very spoiled in the Northeast to have such long records. So you can get much longer records of air temperature and precipitation and some of the meteorological measurements. And it's important to bear that in mind when you start looking at these shorter time intervals, for instance, from the mid 1950s up to the present. If you're talking about precipitation, there was a major drought in the early 1960s that can really kind of influence the trend line. And so it's important to keep that in mind. I think the really unique thing about Hubbard Brook is that it's that so many different things are measured at one place, and that's a really rare thing. And so in the Northeast, and really globally, it's recognized as a place where people are just making all sorts of measurements. Some of them are climate indicators, some are not. But if you look at the complete record, the story is really quite clear. We have things like migratory bird return dates. We make phenological measurements. So we measure the date when leaves come out on trees and when leaves drop in the fall. As I showed, the ice in and ice out dates. And so when you put this complete story together, it's really pretty clear and convincing evidence. But there are definitely longer records of certain things in other places.
Yeah, well, I mean, as ecologists, as environmental scientists, as the work you've both shown, you're looking at a whole host of different variables, certainly not just the physical world and meteorological impacts or anything like that. So I'm sure Hubbard Brook is beneficial for your work there in more ways than one. I have a question and here from Jay that Jay asked, and maybe Alex, I don't know if you want to take a swing at this, but I got curious too. Is there such thing as a summer whiplash?
Yeah, so you could think about whiplash as being any sort of sudden and extreme change in weather. And so actually I don't know where the term weather whiplash first came up. We did a bunch of digging when we first started working on this project. But one of the first places I encountered it in the scientific literature was a paper that came out, I don't know, 5 or 6 years ago, that was describing weather whiplash as this transition from drought to flood. So there's an extreme drought in the Midwest that started early in the growing season, and I don't remember what year. And farmers were going, proceeding, to plant corn and soybeans as they have to do, and they put all this fertilizer on the ground, and then the rains never came. And so the crops just sort of sat there, the fertilizer just sat there, and then there was some pretty extreme precipitation, like rain events, that then, because the soil was so dry and cracked, like the water, like there was a lot of overland flow, and it flushed all these fertilizers into rivers and ended up in the Mississippi, and you could see them all the way in the Gulf of Mexico, right? And so this transition from extreme drought to flood and the impacts on water quality was called whiplash, but this was something that happened in the summer and not in the winter, right? So you can have these extreme swings in any season, really. But then the idea of winter weather whiplash, I first encountered actually in the popular press, where the Capitol Weather Gang in Washington, D.C. was talking about, and I don't remember when this was, this might have been back in 2005 or 2006, this week where, it starts out in February, or March, like really weird, 70 degrees, and you like break out your shorts, and then by the middle of the week, it's, 5 degrees, and you're trying to find your parka again, right? So it could apply in lots of different contexts, right? But I don't know if it started in the media, in science, or if it was sort of a hybrid, but it's, showing up more and more in scientific literature and can be applied to other seasons.
Yeah, and that's sort of my own question that I'd written down here that was sort of related was, I mean, I guess, and this is for both of you, whoever would like to answer. I'm curious, since you've kind of started engaging in this work, where you've seen connections. I mean, I know you're looking largely in some of the work here, the northeastern United States or the eastern US, but where, I don't know, you've seen either interests or connections with other sort of whiplash type investigations happening, in other regions of either the country, continent, or world.
You want to take that, John? You want me to?
That's a tricky one. Yeah, I mean, it's still a relatively new term, I'd say, and it's being used by different people in different ways. And our focus has been on a part of that and really on the winter aspects of it. But there are people studying whiplash events of all times, and you really hear it in the media now all the time. I think there's been less scientific study of it, or at least being termed that. And so, so it's hard to say how far the reach is and beyond what we're doing.
Yeah, I had to ask, even just in thinking more recently and some of the, really headline grabbing snowfall happening out west. I mean, even in Southern California, things like that. That's their climate. What's, either considered normal or typical for their region. Obviously, it's going to be different from here, but I'm sure in those contexts, they're probably thinking about whiplash as well.
When you hear about snow in Los Angeles, that's kind of what you think of, that's immediately what came to mind for me.
Yeah, exactly. I'm not as familiar with that climate, but I have an understanding that's atypical. John, sticking with you just for a second, I'm curious. This is a question from Kim. I know you had mentioned a little bit about, impacts on natural systems, woolly adelgid. So even, I know crops come up quite a bit, but just in any of the investigation work that you've done, whether you've connected or looked at impacts to animals in these whiplash events, if that's come up at all, or interest in studying that in the future.
Yeah, I'm trying to think of it. Can you think of anything, Alex? Nothing's really coming to mind. It hasn't been a big focus of our work to date, but it's certainly something that we could focus on. We do a lot of work at Hubbard Brook on winter climate change and impacts on organisms. And a lot of that work has stemmed from research on soil freezing events, which is related obviously to temperature in the snowpack. And so organisms that overwinter in the snowpack or beneath the snowpack are affected by the depth of the snowpack, obviously. And so there's been quite a bit of work on that. But these extreme kind of events like winter heat waves and moose, there's been a lot of research in that area as well. It's something that we haven't really tackled as part of our research, but it's definitely an interesting topic, and people are working on aspects of it.
Yeah, just to emphasize, that's neither of us are wildlife biologists. We do have colleagues that are trying to understand changing winters and changing winter weather and impacts on wildlife. And you hear about events in other parts of the country. There was a really big rain on snow event last year in Alaska, and then it's cold in Alaska, so the snowpack freezes again. And so if you get changes in not just the depth of the snowpack, but its density and its properties, that can really influence mobility too. So the snow can be a habitat. It's also something that animals have to walk through. And if you get rain on snow and then it freezes, then travel can be really difficult for lots of wildlife. But that's interesting, not our area, right?
Yeah. Oh, sure. Yeah. And I unfortunately won't get to everyone's comments here, but a number of folks in our Q&A bubble here suggesting all sorts of things from, birds, owls, migration, think of the spring peepers. I mean, all those things are, timed with certain, natural world cues. And yeah, even just thinking of Mount Washington, when sadly, when birds get waylaid on Mount Washington, sometimes because of a storm sweeping through, and maybe boy, they really didn't expect to end up on Mount Washington in a snowstorm, but here they are. Another question, actually, and this is once again another nice question from Jack. Shout out to Jack here. Some thoughtful questions tonight. One that I was considering, and I know you touched on briefly at the end, Alex, but around some of your future work, and certainly where you can see the impacts of your work in terms of mitigation or adaptation. Where have Jack, and I've lost your question already, Jack, but where do you see your points of connection, either working with, I don't know, utilities, law enforcement, those folks? I mean, where do you see some of those potential connections, or even, changes or improvements happening maybe in relation to your work?
Yeah, so that's also a little outside my area, but it's really good to have collaborators, right? And a nice interdisciplinary team of collaborators, some of whom really work more directly with people who maybe will make decisions to help make these events less impactful. So one of our collaborators, Anita Morzillo, who's been a co-author on a lot of these papers, she has done a lot of really important research, some of which, related to this 2011 Snowtober snowstorm and Hurricane Sandy, that it really helps to influence power companies making decisions about which trees to cut and when, right? So the aftermath of the Snowtober snowstorm, especially since it fell on the heels of Hurricane Sandy, like really led to some big changes in utility companies and some of the pruning that happens. And so there is a connection there, but it's not one that I have. It's nice to
yeah, sure. Present the data and maybe make recommendations. I recognize maybe above and beyond your area of expertise.
But I also think it's an important question to ask at, as we move forward with this work, at the outset of new projects, like what kinds of information would be most useful for decision making, and can we try to collaborate or deliver that.
Yeah. Well, and so I know we're running we're almost at the end here, and maybe just ask there's so many questions, but might just save one last one here, and certainly could follow up with folks after the fact. But John, I don't know if I forget now who had referenced this, but Janice was interested, had a question here about being able to demonstrate statistically the frequency or magnitude of winter weather whiplash and whether it's increasing over time. I believe there was reference to that as maybe future work and seeing, climatologically how frequently or how intensely these events are occurring is, what does that potentially look like? And I guess, can you speak to that a little bit and its connections with climate change? I know it's hard to tease out.
Yeah, this is so hard to do because, these are rare events by definition. And so, in the record lengths that we have, it's so hard to pick them out when you have so few events. And an example is like, ice storms. And the ice storm of 1998 was a huge event in New Hampshire. We haven't seen one since that, really, at least to that level. And so, it's hard to tell if they're getting more frequent if they're so infrequent in the record. And so that's a really big challenge for us. And it's also a challenge for some of the other things like tornadoes and hurricanes. And that's why we have less confidence in that. We also don't have a lot of good data on some of these events as well. For this project, we had to go to newspaper clippings, which is a really hard thing to kind of quantify, maybe not clippings, but searches. But it's a really hard thing to quantify if you don't have really good solid data to go on. And so we're doing our best, but it's a grand challenge.
Yeah, absolutely. Well, again, thank you, both of you, for sharing your work tonight. I know just since asking you both to present, there's been many different times where I've thought about, oh, good, I'm so glad they're speaking tonight, because this is a topic on the front of my mind as well. And certainly with some of the swings we've seen this winter, I know there are a lot of interested folks who are curious about your work, and happy that you were able to share it tonight. So thanks to both of you. Thanks to everyone else who also joined the program this evening. If you enjoyed tonight's free program, we would encourage you to make a donation to help support programs like these over at mountwashington.org. You can hit the donate button that's in the upper right-hand corner there. If you have some thoughts about tonight's program or suggestions for future program topics, please take some time to fill out the Google Form survey. Let John and Alex know how they did. I'm sure they'd welcome some feedback as well, since they want to communicate their work the best way possible. And if you'd like to follow along for future programs, certainly would encourage you to do so. Go over to mountwashington.org/SITM. Join us for our upcoming programs. April 11th, we'll have Professor of Meteorology Lourdes Aviles from Plymouth State University and Mount Washington Observatory meteorologist Ryan Knapp. We're going to talk all about Aurora Borealis and atmospheric optics. And then on May 23rd, we're looking forward to having Ralph Keeling from the Scripps Institution of Oceanography at UC San Diego, who will talk about long-term trends in atmospheric carbon dioxide. So don't forget to register for those programs, and you can watch any previous programs you may have missed over there at mountwashington.org/SITM. And thank you so much again, Alex. Thank you, John. Hope you both have a great night, and see you all soon. Take care.
Thank you.
Yeah. Bye-bye.